What's going on, everyone? Welcome back. Patrick here, and in this video what we're told is that the function f is continuous and one-to-one on the interval -3 and 5. F of 1 is equal to 4, and then the inverse has a point -3 and 5. Then which statement out of these 5 statements here is true? So let's actually draw a diagram first of what we're working with. So we're told this function is continuous and one-to-one on the interval -3 and 5, so between the x values -3 and 5. We're also told f of 1 is equal to 4, so at an x value 1, we got a y value of 4, so that would be over here. And then we're also told the inverse has a point -3 and 5. Now, if the inverse has a point -3 and 5, then what does that mean for the function? That means the function has a point at 5 and -3. Right? If we interchange the x and y values, so at an x value of 5, the function has a y value of -3, which would be down here. So that's what we know for sure. So we know this point, and then we know between -3 and 5, those x values, the function is continuous and one-to-one. So let's go through each of these statements now, knowing all of this information here, and see which one has to be true for sure. So number one, f only has negative values from the x value 3 and 5. So what that statement is saying is that from 3 to 5, the function only has negative values. And that's not necessarily true because we don't know. We know that this function has to cross the x-axis, okay, between 1 and 5, because we have a point here, we have a point here. So by the intermediate value theorem, it's got to cross at some point, but we're not told when it's going to cross. It could maybe even cross over here, right, between 3 and 5. Let's say it crosses at 4, right? Then there would be positive values between 3 and 5. More specifically, between 3 and 4, there would be positive values. So because we don't know when it's going to cross, we can't necessarily say that f only has negative values from the x value 3 and 5. So that statement is not necessarily true, number one. Number two, f is differentiable on -3 and 5. Now, we're told that it's continuous and we're told that it's one-to-one, but that doesn't necessarily make it differentiable. Now, if a function, we know that a function can be continuous and non-differentiable. We went through a bunch of cases, so we can have like a corner, we could even have a cusp, we could have a vertical tangent, right? Different ways where a function can be continuous and non-differentiable. But we're also told that the function is one-to-one. So it has to pass the horizontal line test. So this is where it's a little tricky, because if it's one-to-one, then it can't have a corner and it can't have a cusp, because then it would fail that horizontal line test. However, one of the cases where a function can be one-to-one, it can be continuous and non-differentiable, is if it has a vertical tangent somewhere, or a better way to show it is like that, right? So there can be a vertical tangent, and notice that this function would be continuous and it would pass that horizontal line test, so it would be one-to-one. So it's possible for a function to be non-differentiable, continuous, and one-to-one. And the vertical tangent is an example of that. So between -3 and 5, if there is a vertical tangent somewhere, it's still going to be continuous, still going to be one-to-one, but it's not going to be differentiable. So it's a potential that the function can be non-differentiable at some point in that interval. And then same thing between 1 and 5. So from here to here, we don't know. There might be a vertical tangent somewhere between 1 and 5. That would make the function non-differentiable, right? It would still be continuous, still be one-to-one, but it can be non-differentiable if it has a vertical tangent. So 2 and 3 aren't necessarily true. Number 4, there exists at least one x value between -3 and 1, where f of x is equal to 0. So between -3 and 1, they're saying there exists at least one x value where f of x is 0, basically where it's going to cross this axis. And notice that that's not necessarily true, because we know that if the function is continuous and it's 1 to 1, then from 1 to 5, okay, we know it's going to cross at some point here. So that means from -3 and 1, notice that the function can't really come back down, because then it would fail that horizontal line test. From here to here, it's got to be going down. So if it came back down for x values less than 1, then notice it would fail that horizontal line test. Right? So we don't know what's happening to the left of 1. The function's going to keep going up here, but it's definitely not going to be passing that axis. So statement 4 wouldn't be true. There exists at least one x value between -3 and 1 where f of x is 0. And then what about statement 5? There exists only one x in between 1 and 5 where f of x is 0. And that statement ends up being true, because between 1 and 5 here, this function has to cross the axis at some point. To get from this point to here, if the function is continuous, it's got to cross at some point. Now, why is it only 1? Why can't it say at least 1? Well, it can't be a case of where there's going to be multiple crossings. Why is that? Because then the function wouldn't be 1 to 1. It would fail that horizontal line test. Okay, so there can only be one x value in between 1 and 5 where it's going to cross that axis. I'm going to show it one more time. So that's kind of the trick of the question. There is only one x value between 1 and 5 where it's going to cross, and it's because number 1 is continuous, so it has to cross. And the reason why there's only one is because it's 1 to 1. So it has to pass that horizontal line test the whole time. And if there were 2 places where it crossed, or 3 places or 4 places, it would fail that horizontal line test. So there can only be one x value where it crosses the axis where that f of x is equal to 0.